Okay, I'm going to get started, and we're going to work from this screen here, since there are not that many people, and you all have good eyes. One last time. Good afternoon. Good afternoon. All right. So, last lecture, and I see not very much interest in history our future scientists have, which is a very, very sad story. Of course, it doesn't surprise me. Our last president didn't have any history background, didn't understand anything about history, made every possible mistake that other people made before him, okay? So I'm not surprised that the students are not interested in history, especially the scientists. So we're going to have very highly educated idiots, essentially, all right? That's what it is. That doesn't apply for you, but it's a very sad story, actually. So what I would like to tell you, about Berkeley and the periodic table. And this is something where you as a Berkeley student can be extremely proud of. And this man here, Glenn T. Seaborg, is one of the major players in that story. He was born in 1912 in Ishpeming. This is in Michigan, a little town in Michigan. And his parents were of Swedish heritage, and they spoke at home only Swedish. Okay, until he finally went to school and learned English. He knew English, some English, but they were very proud of their ancestry. And when he won the Nobel Prize, you have to go to Sweden and deliver a talk. He gave the first paragraph of his talk in Swedish, and the Swedes were very much surprised that such a famous American would know Swedish, and name Seaborg obviously is a Swedish name, and they said he spoke with a perfect southern accent, Swedish southern accent, so he had a heavy accent. That was the area, obviously, where he came from. In 1922, his family moved to Home Gardens near LA. Those from LA probably know where this is. And the family wasn't very well off. His father was a precision mechanic, and after that move, he didn't find any constant job anymore. He had to go from job to job to make a living. And the move was initiated by the mother because she wanted to have the family exposed to much better learning possibilities. And I think it paid off looking at Professor Seaborg. He went to David Starr Jordan High School in Watts. You know where Watts is in Los Angeles? Okay. You live there? Excellent. You know David Starr Jordan High School? It's in Long Beach now, okay. And he developed a very special interest in chemistry and physics, which was attributed to his inspiring school teacher. And this is, for many of you, probably true too. Some of you at least, they had somebody very interesting in school, and that got you into science. So he was the valedictorian of his class, and then he went to UCLA, where he had to work. And he lived at home and commuted. He did all kinds of works. After about getting 94% of this qualifying exam, he was hired as a lab and stockroom assistant, only half-time, of course. And in 1931-32, he was awarded a $150 scholarship, $150. That was a fortune at the time, a handsome sum of money. So he got in 1934, he got his Bachelor of Art in Chemistry, but he took a 5th year to get a master's. And then he looked to Berkeley, and he wanted to go to Berkeley for his PhD, because just like what you said, he described the atmosphere as exciting and glamorous. There's these crazy professors there. And one of the persons that drawn him was G.N. Lewis. You know G.N. Lewis from the Lewis dot structures, among many other things. And E.O. Lawrence, he is the founder of the Lawrence Berkeley National Lab up there on the hill. It was called then the Radiation Lab. He was a professor in physics, and so he got his thesis in 1937 on inelastic scattering of neutrons, and then he became a Lewis assistant, and Lewis was his mentor, G.N. Lewis was his mentor. He became an instructor in 1939 and was promoted to assistant professor in 1941. He already had discovered some elements, okay? And then finally, in 1945, they made him a professor here because he was gone. He already had synthesized plutonium and was responsible that plutonium would be produced in kilogram quantities, okay? So this is how the way was now. Nowadays, if you have a good guy here, or a good person, good professor, they wait for some money from somebody else and say, go, come to our school and do your research here, then we immediately give this person more money to have him stay here. So they had to fight like hell in order to become professors. He was then in 1946 the director of the nuclear chemical research at the radiation laboratory. That was the Lawrence Berkeley lab. That's what he founded, the RAD lab, actually, together with, no, it was founded by Lawrence, but he was the director for chemical research. Anyhow, so this is the man I'm going to talk a lot about, but I will also talk about a lot of other people on this side of the Pacific, of the Atlantic, and on the other side of the Atlantic. And this is how the periodic table looked now. All right? We have 112 elements. 112 just became, got his name. Very recently, the IUPAC accepted this name. 112 is Copernicium, CN chemical symbol. I will talk about this a little bit later. But this was the periodic table before World War II. That means before 1941. And you see, there were some radioactive elements. There was uranium. This was discovered in 1792 in Berlin, Germany, by a club road. And then you have radium and polonium, and radon, which was discovered by Pierre and Marie Curie in 1896 and 98, okay? And I talked to you about this. They received the Nobel Prize for that. And she got a second prize in chemistry in 1911. So there was then thorium was known, and actinium. Actinium is in the natural decay series of thorium, and radium was also a part of a natural decay series, which was discovered by Curie, as I said. But the rest of this doesn't look like the periodic table we see here. The most important thing is this whole row is missing here. And the actinium is here, and the thorium, which stands now here, that stands here as the second. Right there where element 104 is, there stands the thorium, and these other elements are here now, and they are not part of a separate series, all right, just like the lanthanides. And so it began with this gentleman. This was Professor E.O. Lawrence, and he was a professor of physics at the University of California here, and he became the first director of the university's radiation laboratory in 1936, which was actually down here, was not up on the hill. And he invented the cyclotron in 1929, which gave birth to a full, complete new science, the science of these large instruments, accelerators, colliders, which we hear now, super colliders. This was all started by this gentleman, and he also collaborated with his brother, who was the director of the University Medical Physics Lab, to study medical and biological applications of the cyclotron. Very important nowadays. So he was, for this, awarded the Nobel Prize in Physics in 1939, and this is the first cyclotron, okay? This is the first cyclotron that he made, and that he constructed this, and his graduate student, always the graduate student do most of the work, of course. The ideas come sometimes from the boss. And the graduate student was Stanley Livingstone, and this cyclotron was the first of one of those working machines, and I think this is Seaborg's handwriting here. I think when he took a lecture from Lawrence, this is his notebook. And I think, if I remember right, this is Seaborg, and not that I was there, okay, but Seaborg told me. I remember right, this is Seaborg's hand holding that first cyclotron here, and they were accelerating the ions here very quickly, not that quickly. So what did they say? This was able to accelerate protons, very, very light nuclei, to an energy of 80,000 volts. So that's 80,000 electron volts. And they reported the results at the American Physical Society meeting in January 1931. And this got the PhD for Livingston. And Lawrence got $500. $500 was a lot of money from the National Research Council toward a machine that might be useful for nuclear physics, So if somebody tells you something, maybe you can use it, or you probably can't use it. Don't believe anyone. Go whatever you think is right, do it, especially in science. So now that it's bigger now, they became bigger and bigger and bigger, and this was then a 184-inch diameter cyclotron, and these are the magnets here. And this was one of the biggest cyclotrons we had up at the hill. This is now demolished. That's where I think the advanced light source is now. And there is Lawrence here with his team now. So what did they do before 1956 when they had only relatively small cyclotrons? And the first larger cyclotron, which wasn't very large, was at this place here. There's a plaque, if you have seen it, outside of Latimer Hall. There's a plaque, a historical marker. And I believe that this building is, because of this building is designed round to sort of mimic a cyclotron building. And so they were only able to accelerate very light particles like neutrons, hydrogen, deuterium, or helium nuclei. And then after 1956, they could, because they got more and more acceleration power, higher and higher acceleration voltages, they could accelerate heavier particles like carbon, nitrogen, oxygen. And in the 80s, we had what was called the Bevatron, and there was a pre-accelerator, and the HILAC, and there we were able to accelerate uranium-238, and we could let uranium-238 collide with uranium-238. So there was a lot of fundamental nuclear physics done with that. Let's go to Europe. Say the time is 1938, and it's in December 1938, and there's these guys, Otto Hahn and Fritz Strassmann. They worked in the Kaiser Wilhelm Institute in Berlin, in Dahlem, and actually I took this institute, it was in a very old building, I took my organic labs in this institute, okay? I didn't find these guys anymore, of course, hopefully. So they heard about the neutron, and the neutron was discovered in 1931 by Chadwick in England, and they said, if we put a neutron in there, maybe we can make higher nuclides, that we sort of stimulate the nucleus, and we add some nuclear particles, and maybe we can make new elements, okay? And they were trying and trying and trying, and so they used a neutron source and a natural uranium, and then what they found is, they always separated. They found a lighter and a heavier fraction. And of course, Strassmann was not Hahn and Strassmann, they were chemists, they were not physicists, and the education was not as closely together as today, that you study essentially physics if you study chemistry, and you study some chemistry if you study physics. And this was not the case, so he didn't understand very much about physics, and they had a collaborator, which was Lise Meitner, her name. She was a woman from Austria, and she was part Jewish, which was a big problem for her later. And she worked there. Of course, they never had women, very few women working in science. She had to come through the back entrance into the building, because it would not be fitting that a woman worked in a science building. Can you imagine how far you women have come? All right? And so what, just as a sideline, so this is the team here. She started actually in 1914. Actually, the labs look like this when I took my classes there. She started in 1914 with him here, but this is Otto Hahn. And there are the three of them in 1956. There's Hahn, who won the Nobel Prize, actually in 1944. I can't understand why the Swedes would give the Nobel Prize to a German while the World War II is raging all over the place. Yeah, that was very interesting to me somehow, and I never found an explanation for that. So what this guy wrote to her, he said, as he had to go then, she had to leave Germany in that year, and because her life was at stake because of the Nazis. And so she then emigrated to Stockholm, and she corresponded with him. Of course, they didn't have email, that was regular mail. They were corresponding with mail, and there was the telephone, but it was pretty difficult to call out of Germany and into Germany. And so he wrote to her, and he said, I have no idea. I can't make any sense out of this. Our new elements, there's one heavier and one lighter element. And this is the fractions, so they co-precipitate this with a certain fraction, and they co-precipitated this co-precipitated with the barium co-precipitate. It's a long story. I could tell an hour about this by itself. But so she was then at Christmas in Denmark with her nephew. Her nephew was Frisch. Max Frisch was became a very famous physicist. And they were walking on the beach in Denmark Christmas Day. That's at least what the story says. And they were talking about this back and forth about these funny experiments. And then she came up and said, you know, what is if the nucleus just explodes and makes two fragments out of it? And she wrote him back and said, you know, you got to check this. And so this was when they did in December 16, actually. And then in January, February, he went back into the lab, or shortly after Christmas when he got the letter, he went back into the lab. And sure enough, he said there was one lighter and one heavier fraction. And so with this team, with the help of Lise Meitner, had discovered nuclear fission, all right? So that you can fission a nucleus into two particles, and they didn't know at the time that there would be so much energy released from the reformation of the fission products. But so that was the time when fission was discovered in December 16, 1938, actually. And so now there was this guy, Edwin Macmillan. He was a young professor here in Berkeley in physics, and he was a tinkerer and made all kinds of funny machines. You know, like you've probably seen this. You drop a ball on one, a little marble on one side. It goes all the way around, and then at the end, it matched a match was struck, and it lit his cigarette or his pipe or whatever. Okay, so he said, you know, there got to be something when I use these neutrons, and they have these fractions. It fractionates that nucleus. I should be able to calculate or to measure the energy that these fission products have, these two products. What kind of energy? I know about the energy of the neutron, but I need to know, or like to know, what the energy of the fission products is. And so he did that, and this is him here in 1940 in one of the labs around here. I think it's in Lewis Hall. And what he did is he put a stack of, he was a chain smoker, okay? And he rolled his own cigarettes. So he said, why don't I make a big stack of cigarette paper behind there, and then I can disassemble, and I do that fission experiment, and then I catch these fission products into this stack of cigarette paper, and then afterwards I disassemble them one after the other and see where it went, and then I can calculate the density of that whole thing, and I can calculate what the energy must have been in order to get there. With this, he would have gotten the fission fragment energy. So he did that, and fortunately he had this very good graduate student, Abelson, who was also a very good chemist, and he dissolved one layer after the other to measure the radioactivity. And what this guy found, Abelson, that they find some new radioactivity. Suddenly this thing is decaying what they had. So there was something in the paper, they dissolved it and put it in front of a counter, and it was counting and decaying. And with this, actually, they discovered the first new element, man-made new element. This was element number 93. It beta decayed. Remember beta decay? It beta decayed. Uranium-239 they used 238 and bombarded with neutrons. That made uranium-239, which is unstable. And this beta decays now. What does it do? It goes one up in the set here. It goes to 93, 239. And this half-life, they measured 23 minutes. And that beta decayed then with a half-life of 2.3 days into element number 94, 239. They didn't conclude that one, but they found this element. And this element number 93, if you look here, 93 is down here, is called neptunium, all right? So they wanted to measure the fission energy, and they discovered a new element. The guys in Germany, they wanted to make new elements, and they discovered the fission, okay? So let that be a hint for you. If you see something in your experiments that you can't make sense out of it, maybe you are up to a very big discovery. You got to look from it from all sides, okay? That's very important. Most of the very famous discoveries were made out of accidents, all right? But the people were so well trained and such good scientists that they could look at it and say, you know, this is what happened. And so with this, they had big discoveries. And this is still possible nowadays. So let that be a lesson for you. And so they discovered that element. There's Phil Abelson. He got his PhD for this. and was the co-discoverer of neptunium in 1940. Of course, Seaborg was part of this, and no, Seaborg wasn't part of this yet. So there comes Seaborg into play now. Seaborg was in Berkeley already, and this guy Macmillan, he was a genius actually. So they called him, the military called him, to invent a landing system for the military airplanes when the weather was bad. So essentially he invented radar landing systems for airplanes between 1941 and 1945. So Seaborg, and he came then back here as a professor again, and Seaborg asked him if he could continue this kind of work while he's gone, if he would mind if he continued this work. And he said, no, go ahead, right ahead. It seems to be interesting work, just do it. And so this is Seaborg now in 1941 here at Gilman Hall over there, where he works. This was a counter, a nuclear counter. As you've seen, they're much smaller now. I brought them here, a little thing I held in my hand. So what they did then, Seaborg was then in charge, and he is on the paper, but he would, with Kennedy and Arthur Wall, they all became famous professors later. They were graduate students and postdocs. He bombarded uranium-238. He said, I use something heavier now. Maybe I can make a heavier element. And so he used now hydrogen nuclei to bombard this, heavy hydrogen, of course, deuterium. And with this, he made element number 93, and this spit out 2 neutrons to give element number 93-238, and this decayed with a half-life of about 2 days, beta decayed to element number 94-238, not 239, which we know, and this has a half-life of 50, they discovered a half-life of 50 years, and this decays by alpha decay. And we know that the half-life is now 83 years, okay? That was very good. They had nothing, essentially, and they determined the half-life for this. So now, then later on, they made uranium-238, used uranium-238 and neutrons. They made uranium-239, and 239 has a double beta decay. Remember, that was what Macmillan actually did. And it has a double beta decay to element number 94, and this is 239 years, 239 element number 94, and it has a half-life, they determined the half-life of 30,000 years, and it has a half-life of 24,000 years. Okay, so there they are, and they won the Nobel Prize for this in 1951, and there they are with this cigar box, and the cigar box used to belongs to used to belong to G.N. Lewis, the one with the Lewis acids and bases. He also was a chain smoker. They were smoking while they were lecturing, actually. Okay, I remember this when I was a student. Our teachers did that too. They were smoking while they were lecturing, and the students were smoking. But they couldn't see anybody because there was no air conditioning. Anyhow, so this is he used to smoke these stogies. 5 cents was pretty expensive. He had them imported, as I heard, or imported from some South American country, and it was not Cuba. And so they used these boxes to store all kinds of things. And their first plutonium sample that they had, isolated essentially, was in such a box, and if you go into the Smithsonian, you will see that box, okay? That box with that first plutonium sample. So then they needed to step it up because there was the Manhattan Project coming up. The Manhattan Project was the project to build atomic weapons, 2 atomic weapons in the United States to fight the Germans, okay, and to destroy the Germans, and insofar they were very lucky. They ran out of speed and juice before the bomb was ready, so the Japanese had to pay the price for that, okay? So they needed to test that bomb. Actually, the place in Germany that was selected was Stuttgart. It lays in a funnel, and it lays on the bottom. The city is on the bottom of a geologic funnel. And so they said, if we throw it in there, then the pressure wave will also kill the rest of the people, not just the explosion. But this is war, okay? So if you don't want to be involved with it, don't start one. So, and they then had 0.5 micrograms. They used 3 pounds and made 0.5 micrograms of plutonium-239. And this was still not weighable, and they then, no, that was afterwards, the 0.5 micrograms. And in order to weigh something, they had to make a balance that could weigh such small quantities. They designed a balance that could weigh these quantities, and in 1942, then for the first time, they isolated 2.7 micrograms of plutonium dioxide, which is, this is the tip of a forceps. This is a piece of platinum metal, and this here is the plutonium, 2.7 micrograms, okay? But they were talking already about a plutonium bomb, but they had no idea how to really make this much plutonium. And so he went then to the University of Chicago, and that's where was the metallurgical lab, and he started working on the Manhattan Project to produce that plutonium. And so let's go on. Now let's go back to Europe, and let's go back to the year 1934. You heard about the fission, discovery of fission and discovery of the new element. They all wanted to do something else, and the most important false result came from this gentleman here. His name is the very famous Enrico Fermi, and he was a professor at the university in Italy, and he heard of the discovery of the neutron in 1931, and he immediately said, you know, maybe they have an energy distribution. You know, if I take this and bombard uranium with it, maybe I can get an energy distribution. And so he found an energy distribution. When they hit the table, they changed the energy. Okay, they had a wooden experimental table, they changed the energy. He said, okay, now I'm ready to make some new elements. And so he bombarded uranium with neutrons, and he found all these beta activities, and these are the half-lives that he had. And he said, I have new elements. Okay, he didn't have a good chemist there, so he could look for all this stuff. So what do you think he had discovered? He had discovered fission in 1934. So he thought he had made new elements, and he won the Nobel Prize for this in 1938 for new elements, for his demonstration of the existence for new radioactive elements produced by neutron irradiation, and for his related discovery of nuclear reactions brought about by slow neutrons. Okay, so he was then a professor at physics in Columbia University and a professor at the University of Chicago at the Institute for Nuclear Studies till 1954. So he's a very important, very famous person. But you know, these elements that he thought were new, they were not new, they were known, there were these distribution of fission product, let's say krypton and barium, and they were all known, okay? So he didn't discover anything new. He discovered that there was radioactivity, but he did not make any new elements. So he had, in 1934, he had the chance to discover fission, okay? He didn't discover anything, essentially, except that you can make nuclear reactions, but he was a very, very gifted and famous person, which you will see why in a second. So it is now, let's go back in time, for we were in 42 already, let's go back in time to 1939, and this, remember 1938, at the end of 1938, the Germans had discovered fission, and Einstein and his colleagues immediately seen the potential to use this for a bomb, okay? And he sent a letter to President Roosevelt on August 2nd, 1939, to suggest that he needs to make a bomb program to counter the Germans, okay, to get this bomb before the Germans have that bomb. And this is the letter. You can't see it, but it's a very short letter to President Franklin D. Roosevelt, and where he says we need to get started with a program to make that bomb. But this became the Manhattan Project, all right? The Manhattan Project was up in Hanford. This is in the state of Washington, in the desert out there. Then they went to Los Alamos, also where nobody lived, actually out in the other desert. And then they went in the jungle of Oak Ridge. These were the three main players there who were producing the material for the bomb and were doing the research for it. So the first nuclear reactor was then done, and there are no pictures, unfortunately, was then done, assembled by Fermi and his colleagues under the squash court at the University of Chicago. So they went under the squash court there somehow. There was a room, and this is that room here. And they piled up the uranium in blocks in the middle. And it was natural uranium, essentially. And then they had graphite blocks around there to moderate and to contain the neutrons. And so what happened there is they had some rods here which are neutron absorbers. And if you put these rods in there, the reaction doesn't start. So if you put them out a little bit, some of the neutrons don't get absorbed, and they can start reacting with the other uranium, and so on and so on. So there was Fermi sitting, they had a counter attached to this, and the counter must be sitting here. That's what these guys are watching here. And Fermi was sitting here. I don't know which one is Fermi. Never met him personally. But he was sitting there and was calculating how much they should pull this rod out here, okay, to get a certain neutron flux, a certain neutron production. And so he said, okay, pull it out a quarter inch, and they pulled it out a quarter inch, and he was predicting what the flux would be. And on their flux meter, their neutron meter, they could see the flux was exactly there where he predicted. And so they had the first reactor, nuclear reactor. This was again in December of 1942. Remember, fission in 1938, and this is in December 1942. Obviously, good things happen in December in this field. And so I'm waiting every December if something good happens in my lab, but so far, lots of good things have happened, but not the big thing, you know. We're always waiting for the big thing, aren't we? Yeah. That's why we became scientists. We want to make the world better. Yeah. And so there's a good story. I studied chemistry, I studied nuclear chemistry at the Free University in Berlin. That was the western part of Berlin, where they belonged to the Federal Republic of Germany. Actually, it didn't belong to that. It was actually a free state. It was occupied by the Americans, by the French, the Russians, and the British. And the Russian part belonged to East Germany, which belonged to the rest of the communist Germany. And the three other allies, the Western allies, they split West Berlin, and so you could move freely there. And when I was going at the taking lectures from actually I was helping him doing the slides. And the way we had slides at the time, so I was pushing the slides for his lecture. And so that's what happens if you're an assistant. You know, if you're a graduate student, you always have to do something for the professor. I have some people sitting up there who will work for me. They know that very well. And they are not graduate students, though. And so what you see these two or three guys up here, and there's a contraption there. And so he was telling this story, and he was saying, you know, there were 2 or 3 prisoners. They were lifers. They got them from prison, and they said, if you go up there and you get a bucket of boron trifluoride, okay, which if the reaction goes haywire, if they can't stop the neutrons, you put boron on there, and the boron absorbs the neutrons, so they could stop it that way. And so they had supposedly have this hanging here, a bucket on some kind of a contraption, and they had an axe to whack it. And nobody knew, of course, if they would all be alive after the experiment was done. And so this is the only time, I thought the guy was making it up, my professor. He said that was so entertaining. He said there were these guys up there, and I never ever read anything about it or seen anything about it except this one picture. And so there they are, okay? And obviously they got granted then freedom after that. So that was a pretty good deal they got, actually. They gambled nicely. So let's come back to the first weighable amounts of 2.7 micrograms of plutonium. I knew Seaborg quite well, and at the times when I came to, about 30 years ago, when I came to the Lawrence Berkeley lab, you would go in the cafeteria and have your tray, and there would be 6 or 7 Nobel Prize winners having lunch with you there, okay? And you could and they were very approachable. You just sit down with Seaborg. I always sat down. And one time I remember Seaborg was telling me, I said, you know, we had this 2.7 micrograms isolated. And there's this General Groves. Groves was the leader of the Manhattan Project. And this Martin Luther King Street used to be Grove Street. Some of them say still it says Old Grove Street underneath. And so this was named after them. Of course, in Berkeley, they don't want to have a military general. They're having a street. So what happened then is he said, you know, the Groves asked me, Seaborg, you need to tell me, I need to build that building, and you need to tell me how big you want that building. And he said, I had no idea. We had 2.7 milligrams. I mostly doubted that we ever will be able to get much larger amounts, you know. And he said, but he didn't want to tell this guy, okay, otherwise the whole project goes kaput. And so he told him, and he was a football fan, an avid football fan, and he told him, oh, make it about the size of a football field, okay? And sure enough, that was the building, okay? That was from 1945, so that was then the B plant processed plutonium at Hanford, and they used a certain process then later on. No, actually, that was when they processed the plutonium for the bomb, the one which fell on the 9th of August of 1945 onto Hiroshima. Yeah. Okay, and so you see this, there are some cars here, and I mean, this is a huge, huge building. That's what they thought big. They thought big. They wanted to get that done. All right, that's in Hanford, up in the state of Washington. And so now we have that bomb business is sort of done, but they want to do some science also. And they continued to do some science, and they discovered curium in 1944, and in 1945 they discovered americium. They used plutonium and bombarded it with helium particles, and they made curium element number 96242, and that has a alpha half-life of 163 days in this case. And this was done at the Met Lab it was done at the cyclotron here in Berkeley, up on the hill, and then they shipped the sample to Chicago to separate it. I mean, you have to imagine, you use a large amount, and you have this minute quantity that you make. It's like you're looking chemically for a needle in a haystack. So you need to make separation after separation after separation to make sure that you get that. And so then they discovered americium. They discovered actually element number 95 before 96, after 96. There was Al Giorgio was a very important person, and Seaborg, of course, and they did irradiate this in a reactor where they got the neutrons from a reactor. There was a neutron reaction. They irradiated plutonium-239 with neutrons, and it gives off a gamma, and then it beta decays to americium-241, which is element number 95, and there's a half-life of 430 years. So they discovered that. But then they said, oh, we're going to go on, and we're going to make new elements. Now we are already warmed up. Let's make new elements, and they should be fine. So they do these bombardments, and they can't find any new elements. They use the same separation process, but they can't isolate any new activities when they use other projectiles to make new, higher C elements. So what then Seaborg started thinking, he said, maybe they don't behave like these homologues here, which they were looking for. Maybe they behave differently in terms, and he thought about the lanthanides, okay? And he said, maybe we're doing the wrong chemistry. The chemistry that we are using, we separate this one oxidation state, and this plutonium has a very high oxidation state, and you can separate it from all this stuff which you don't need, which has a lower oxidation state, and you do this often enough, that way you can separate very nicely. So let's hear what he said. I have a video here. It's a little old, but it's not my fault. And let's see, I need to get the sound on here. Let's see what Professor Seaborg had. Are we ready up there? Good.
When we at the Metallurgical Laboratory of the University of Chicago went on to try to synthesize and chemically identify the next two elements, they would be the elements with the atomic numbers 95 and 96, we failed. We didn't have the correct predictions for the chemical properties. You couldn't find them without making a chemical separation, because they would be buried in all the radioactivity of the fission products and so forth. And it wasn't until the summer of 1944 that I got the idea that the periodic table was wrong, and that we should take all of the elements, thorium, protactinium, uranium, neptunium, and plutonium, and place them in a separate family at the bottom of the periodic table, a family like the rare earth elements, which we call the lanthanide elements, like lanthanum in the chemical properties. When we used this theory, we could chemically identify the elements, and we discovered the next two elements following their transmutation, the elements with the atomic numbers 95 and 96. And as a result of this, it was possible to go on and predict the chemical properties of the elements following 96. And so that 97, the next element with the atomic number 97 would be like chemically like terbium. And then 98 would be chemically like dysprosium. 99 chemically like holmium, and 100 chemically like erbium, and so forth until you got to the end of the series, which would be the element with the atomic number 103, which would be chemically like lutetium. This made it possible to predict the chemical properties of all of these elements beyond element 96, and then in the ensuing years, we were able to synthesize them and chemically identify them on the basis of the power and the validity of my actinide concept.
So this was Seaborg in the late 70s or early 80s. He was already in his late 70s and early 80s, something like this, in years. And they told him, actually, don't publish this. Don't say this. You will ruin your whole career as a professor. He said, I don't have any career. I have your whole reputation. He said, I don't have much of a reputation, which is, of course, a lie. You know, he already discovered plutonium. And he said, you will ruin your reputation. Nevertheless, he came up with that concept, published it, and this has helped then to discover these elements and reshape the periodic table. So what and actually I misspoke here, this happened already when we are for the discovery of curium and americium. So they had, that curium and americium is after plutonium. Plutonium can be oxidation state 6, but curium and americium can only have oxidation state 3, just like the lanthanides. And this is why they needed a different process to separate those out. The concept that he described helped them to discover curium and americium. So now he discovered all these elements where Seaborg was part of it, and they are all discovered here with participation of Berkeley, major participation of Berkeley, or at Berkeley directly. So there's technetium, which was actually separated in Italy but irradiated here, astatine. Then we come to the actinides, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. And we are stopping here with the actinides. And now we go to the main group elements again, element 104. That's a homologue of titanium, zirconium, and hafnium. Element 104, you know what homologues are. And so this is rutherfordium, and this element number 105, we lost. The official name is now dubnium. We conceded this to the Russians in the IUPAC meeting. And then element number 106 was in 1997, it became officially the element 106 called Seaborgium, and here is Seaborg in his office pointing at this element. And he was extremely proud of that. He said, you know, these Nobel Prizes, you know, no big deal, he says. They're going to run out of money in a couple of hundred years. There will be no more Nobel Prize. But I have the feeling that people will still use something like the periodic table in 500 years or 800 years because the substances are not changing, okay? And so my name will be in there, he said. And he was so proud he couldn't believe it that he had his name in there. And I have another story. Okay, when they were here, they were curium and then berkelium, californium. So there was an article in the New York Times who told them when they had element number 97 and 98, they said, you know, these guys could have called in number 97 universitum, number 98 ophium, and then number 99 or number 90, the other number, the next number, berkelium. Okay, and or universium ophium californium. That's one or the other. And Seaborg wrote back, said, we are not stupid. We didn't have that last element, and we don't want to say universium ophium, and then you guys come and say New Yorkium. Okay, so that's the story he always liked to tell. And so he used to give that lecture actually here, and for many, many years, to always the freshman lecture, and I am sort of continuing this tradition. Of course, now I talk about him. He used to talk about himself too, so that's a different story. But I have nothing to tell about myself. So good. So he then also had isotopes in radio isotopes. He did iron 59, cobalt 60, iodine 131. This is what he used for thyroid cancer and thyroid treatment. And the first patient was his mother. The mother had thyroid cancer, and they treated her successfully with iodine 131. And she lived some significant time after that. Then technetium 99, he did this together with Segre. That's the imaging and also a treatment agent for thyroid imaging for thyroid and treatment for thyroid. Okay. So these are the radionuclides that are used in medicine. That are many of them are used today still in medicine. That where Seaborg was involved in the discovery, a true giant. So there he is, the 10 outstanding young men in 1947. There he is. You know who this guy is? Tricky Dick, Richard Nixon, yeah? Richard Nixon, okay? The president who they chased out of office, okay? And then he became chancellor of the University of California here at Berkeley, and he was an absolute football fan and all sports. He fired all the coaches which were not successful, and I think the only time they won a big championship is that true? They won the Rose Bowl with him as chancellor. And I remember going to parties with him, and he would, it was in the 80s, and there would be on the television, there was in Professor Hoffman's house, on the television, there was the baseball season going on, and he was talking with somebody here, and was talking with somebody here, and then he was watching baseball. And then he was an absolute multitasker. He had 4 or 5 children, if I recall right, and so he is known to sit at home, watch the game, have the baby on the lap, and correct some papers his students wrote, okay? So that's a multitasker, all right. So then the element number 106 was discovered by using californium, bombarding it with oxygen, or curium with neon, and so this 106 decays, then alpha decays to rutherfordium, and this to nobelium, and then to fermium. So this is the team that was done by a team from Livermore and Lawrence Berkeley Lab in 1974. This is Al Giorso, and this is Seaborg. They must have been wearing funny hats for the reason of celebration or something. And this is the confirmation team. This is Ken Gregorich. This is Al Giorso. He was on the team. Ken Gregorich works with me now. And this is Professor Hoffman here, and this is Professor Seaborg. And the people were always commenting about the difference in height. And so they were very good friends, and Professor Hoffman is still very active in science. There are many other people who are in very high positions and I know them personally actually, in very high positions in the Department of Energy and in industry. This is Mary Nye. She's an associate director of the Los Alamos National Lab, okay? She worked in my lab when I was working up there. Okay, let me tell you a little bit more about, Seaborg, he had national service with 11 presidents, actually. So these are the presidents he worked with. He was the head of what is now the Department of Energy. It was the Atomic Energy Agency, or the Atomic Energy AECE. And what? I'm going to do it here. This is so important, I can't believe this. That's my finish. So, he said something very interesting. Look at this here. This is in hieroglyphia. So he said, and he wrote this in his acceptance speech as chancellor in Berkeley in 1958. And this is, you are obviously interested, have a wider interest in things, which is very good. This I would like to say to the people who didn't come today, all right? Not all of them, but some of them. I would like to say, with his words, there's beauty in discovery. There's mathematics and music, a kinship of science and poetry in the description of nature, an exquisite form in a molecule. Now listen carefully. Attempts to place different disciplines in different camps are revealed as artificial in the face of the unity of knowledge. All literate men, and I add here women, are sustained by the philosopher, the historian, the political analyst, the economist, the scientist, the poet, the artisan, and a musician. And I would like to give you this on your way in your life, and I enjoyed teaching you, and I wish you the best of luck.